Let's walk through a hypothesis testing scenario. We're going to complete very familiar calculations from stage 1 and also our degrees of freedom that we've just learned about. We're going to complete the Anova table, so have yours ready if you don't have it out, and then we'll make a decision about the results. So here is an Anova setup for us. We have a 2x3 Anova. Factor A is task difficulty, how hard something is to do. And factor B is fatigue, how tired somebody is. And the dependent variable is the number of errors somebody makes on, let's say, a test. So how hard something is factor A, factor B is the level of fatigue, and the dependent variable is the number of errors. So I've done a couple of different things. One of the things I've done is I've added up the treatment totals for the rows. So as you'll look, treatment for easy task, low fatigue, the treatment total is 15, plus the next treatment total of 25 plus 50 gives us a total treatment total of 90. And you can add the treatment totals of the second row to get a treatment total of 30. So that is our treatment total there. We also have a treatment total at the very bottom for the different columns. If you add up the treatment totals here, we get 20, 40, and 60. And you'll notice that the treatment totals at the bottom equal the treatment totals on the side. And if we add them all together, this equals 120, and these two together equal 120. So our grand total, the long story short, is 120. We have 30 people in the study, and the sum of our squared scores is 860. So the first thing I'm going to do is I'm going to do some of the stage 1 calculations. The first thing I'm going to do is my sums of squares total, which, if you remember the formula, it's the sum of the squared scores minus the grand total squared divided by the total n. So in our study, the sum of the squared scores I gave you was 860. And our G was 120, so we're going to look at 120 squared divided by our N of 30. We can do all this. So this is 860 minus 120 squared. Let me do that in my head right now. 14,400. You know I didn't do that in my head, right? Okay, divided by our N of 30. So we have 860 minus 14,400 divided by 30, which just happens to be 480. Again, I didn't know that off the top of my head. I did do this earlier. So 860 minus 480 is 380. So I now know that my sums of squares total is 380. The next thing we'll do is our sums of squares within. And to get this, we're just going to add up the sums of squares in each of those cells. I've already calculated those for you, so I'm going to write down what those were from the last slide. It was 18 plus 28 plus 26 plus 8 plus 20 plus 20. So our total sums of squares within adds up to 120. And finally, for our sums of squares between, we figure that out by simply subtracting the sums of squares within from the sums of squares total, because we know that sums of squares within and sums of squares between have to equal sums of squares total. So what is 380 minus 120? That leaves us with sums of squares between of 260. Okay, now that we have that, we're going to find our degrees of freedom for stage 1. Degrees of freedom total, degrees of freedom within, and degrees of freedom between. So degrees of freedom total is going to be n minus 1. If you recall, we had 30 participants. Minus 1 gives us a degrees of freedom total of 29. Our degrees of freedom within are going to be basically n minus k, or n minus the number of treatment conditions that we have. We had, how many did we have? We had 6 different treatment conditions. So our degrees of freedom within are 24. I happen to know that between and within have to add up to 29, so I know it's going to be 5, but It's the number of conditions minus 1 for degrees of freedom between we have 5. So let's put this all on the chart. As a reminder, this is how we found our sums of squares total. This is how we found the sums of squared inside each treatment. And the sums of squares between, we just figured out what was left over. For degrees of freedom, this is a reminder of what we've just done as well. And now I have everything on the actual Anova tracker. So we have our between treatment, our within treatment and total for sums of squares and degrees of freedom. We've done stage 1 now. Now it's time to go ahead and move on to stage 2 and look at the degrees of freedom for factor A, factor B, and for the interaction. So you do not need to know sums of squares for factor A. I'm just not going to make you do that. I'm going to just show you how I got it, but sums of squares for factor A are going to be 120, and sums of squares for factor B are going to be 80. And finally, you don't have to do this, but to find the sums of squares for the interaction, you would take the sums of squares between and subtract out the sums of squares A and sums of squares B, and you would have it. But you don't need it because I just put it there for you. I put everything on the chart. Well, not everything. We are missing A times B. So as a reminder, if we take 260, we subtract 120, and we subtract 80, we end up then with 60 for the interaction. All of these 3 columns need to add up to this between treatment. All right, we've made good progress. Now we need to find our degrees of freedom for the stage 2. Let's do that. Degrees of freedom for factor A. If you will recall, we actually had 2 different rows. So degrees of freedom for A is going to be 2 minus 1, or degrees of freedom for A is 1. Degrees of freedom for factor B is a matter of the number of columns minus 1. We had 3 different columns minus 1. So our degrees of freedom for factor B is 2. And then finally, our degrees of freedom for the interaction is a matter of taking our total degrees of freedom for the study, which is 5, minus the degrees of freedom A, which is 1, minus the degrees of freedom B, which is 2. So that leaves us with 2 for the interaction. And here's just a summary of what that looks like. Now I have everything I need to be able to conduct our mean squares calculations. We can follow the logic of this table to figure out the mean squares. We need to find the mean squares for factor A, factor B, A times B, and within treatment. So let's do that. So the mean squares for A involves taking the sum of squares for A of 120 divided by the degrees of freedom for A, which was 1, which gives us mean squares of 120 for factor A. For factor B, we had a sum of squares of 80 divided by degrees of freedom 2, and that gave us a mean squares of B of 40. The mean squares for the interaction, we had sums of squares of 60 divided by 2 gives us 30. We're not done though, because we need to find the mean squares within. And that's found by taking the sum of squares of 120 divided by the degrees of freedom for mean squares within of 24, which gives us a mean squares within of 5. All right, so now we have our mean squares. That's all we need for our F calculations. But first, here's a reminder of what we just did. We took the sums of squares divided by the degrees of freedom for each of these 4 different calculations. All right, I've plugged everything we need into the table, and now the last step is going to be to compute an F score for each of the hypotheses. So let's do that. For each of these F calculations, I know that my denominator is going to be my mean squares within. And so my mean squares within was 5, so I'm going to put that in the denominator for all of these things. Now for the numerator, for factor A, we had a mean squares of 120. So 5 goes into 120 24 times. So we have an F statistic of 24 for factor A. For factor B, our mean squares were 40 divided by 5, which gives us a F score of 8 for factor B. And for the interaction, our mean squares were 30 divided by 5, gives us an F score of 6 for the interaction. Okay, I've just plugged these into our chart, and I've also added the degrees of freedom for each. So for factor A, we have 1 in 24 degrees of freedom with an F statistic of 24. Factor B, 2 in 24 degrees of freedom, F score of 8. And the interaction, 2 in 24 degrees of freedom with an F of 6. These are the 3 hypotheses we're going to check. How do we check them? Well, we have to look at our F table to see if our F statistics are statistically significant. Do they exceed the critical values at these degrees of freedom? So when we're analyzing a factorial ANOVA, we're asking 2 questions. Do either of the independent variables produce a statistically significant treatment effect? Remember, those are called main effects. And then we talk about whether the 2 independent variables influence another or remain independent. Is there an interaction, in other words? So for factor A, we actually reject the null hypothesis. There is a statistically significant difference in performance according to task difficulty. For factor B, we also reject the null hypothesis. There's a statistically significant difference in performance according to fatigue level. And finally, there is an interaction effect. There is a statistically significant interaction between task difficulty and performance. But I have to tell you that we have to actually look at the matrix to see where that difference is or where that interaction is. So let's look for where the unusual result is. So we were counting the number of errors that people were making. And it seems that errors are made more progressively as you get more tired. So people start off with 3 errors and they go up to 10 errors when they are extremely fatigued. This pattern starts again in the second row. However, all of a sudden it drops off. We would expect this to be higher than 3, but it's actually lower than 3. This is an unusual, unexpected result. And what's happening here is maybe, I'm guessing, that when you have an extremely difficult task and you're very tired, maybe some sort of adrenaline kicks in and you're able to do a little better than you might be expected to do normally. I'm not sure, but this is an example of an interaction. It's an unexpected event that when one factor depends on the other. All right, that's it for now. In the next video, we're going to talk about effect size and eta squared.